Today, as I was saying, we would much prefer to use Spark. It's going to be a much friendly interface and allow us to avoid all those low-level stringing things together and mapping our problem into a different, maybe less natural paradigm. We're going to use Spark not only for those user-friendliness reasons, but also because it learned an awful lot. It benefited from being a much newer technology than Hadoop and learning from its lessons. It's also much higher performing. It has learned in particular the fact that, and takes for granted the fact that modern computers have a lot more RAM than they used to the point where today, even fairly large data sets, many terabyte data sets, can fit entirely into RAM. And if you can fit your data set into RAM, then that's a good thing. You can juggle it and analyze it and work on it much more quickly. So we're going to do that. As I was saying, the ability for Spark to use RAM efficiently is really important because today we have lots of RAM. And anything sitting in RAM is obviously going to be much faster than anything sitting in disk. Hadoop did everything in disk, assumed everything went from one stage to the next in disk and staged things through disk. And so it was just handicapped greatly by that. Also, Hadoop didn't have the ability to do a lot of more clever behind the scenes optimization from one stage to the next of data manipulation. Spark is a master at that. Spark will do very lazy evaluation. We'll see what that means as we start to use it, which means it defers doing any data shuffling and analysis and movement until the last moment. And by doing that, it can combine things and do shortcuts that are extremely effective with big data sets. We'll see that in action as we go along. But these two capabilities greatly increase the performance of Spark over what you could do with Hadoop. Now, at the same time, they took the opportunity to update the way that you interact with Spark. So it has a very nice, friendly, high-level API that we're going to use, mostly in its Python mode, but also Scala and Java are first-class citizens. It's actually written in Scala. But these are all supported as first-class citizens, and there are other ways to access Spark as well. But we're going to use the Python API. We'll find out it's very friendly and high-level. We can do things interactively in a nice Python shell. So that is a wonderful advance over the traditional Hadoop way of doing things. And also, it rolls into it a lot of the components for using more complex data paradigms, like we talked about streaming briefly earlier, data that's constantly coming through, dealing with things at the high level like SQL-oriented data in databases, machine learning algorithms, graph databases. Spark anticipates that we're going to deal with data in these kind of fashions and formats. And so it gives us nice APIs and nice methods for dealing with this stuff at a high level. We don't have to cobble together our own methods for dealing with this stuff. Hadoop had lots of pieces that it did eventually manage to make work with this, but Spark has this kind of built-in anticipation. But once again, Hadoop as the disk system behind all this, the HDFS file system behind this, is a very, very common and sensible way to go. So these pieces from Hadoop are useful. Here's the actual way that Spark operates on stuff, is that we're going to sit and write some very simple looking, nice, friendly scripts that are going to live on the driver, the front end here. But when things run and need to run in parallel, behind the scenes, unbeknownst to us, or at least it's not our foremost concern to worry about it, we're going to have all this parallel machinery that Spark is going to be conducting and managing. And as long as we put our data into the right data structure, what's called an RDD, this will all happen automatically. So if we make sure that our data lives in these Spark data containers, resilient distributed data sets, then automatically, whenever we do operations on these data sets, they're going to go and in parallel use the many cores that are available in the compute system behind the scenes. And that might be, in our case today, just dozens of cores. You've got a single node on bridges, but it could be many thousands or millions of cores on a big machine. It will, as much as possible, keep that data in RAM. If the data set's too big, it will have to shuffle things, but it will do that for us behind the scenes. So it will try to keep the data in RAM as much as possible to be efficient. It will overflow things to disk where necessary, and it will do all of this for us automatically behind the curtains. It will manage this. This is a wonderful thing. As long as our data lives in an RDD, the whole Spark system is at our fingertips and will be automatically used. The Spark formula to keep things in the RDDs and manipulate them there is that the first thing we want to do typically at the beginning of some Spark script that we've written, program we've written here, is we want to load the data into an RDD. And we'll see there are many ways to do that. And Spark has a lot of connectors to just suck data in right out of a database. So if you've got stuff sitting in a Mongo database, it can just go and grab that data directly. That was an earlier question, and we'll come back and answer the specific questions. But one of the earlier chat questions was, can we access stuff from Spark that's in databases do we have to convert? No, Spark can go and suck stuff out of many, many different data formats because it's got all these connectors. It's a very mature and well-developed ecosystem. So we load data into an RDD one way or another. We can do it manually ourselves. We'll do that for some more simple exercises. Once it's in our RDDs, then we can do in parallel, without us having to think about it, a lot of stuff. And transforms are the number one way that we do stuff on our data. We say, okay, take the data and transform it in some manner. So for example, let's say we've read in to our database a visitor address log to our web page. And let's say we want to filter out for purposes, whatever purpose, we want to filter out all the non-US visitors. So that kind of filter is a transform that we can do on the data. So we'll have some very simple, friendly commands that we can do to manipulate our data set. And then all this will happen automatically in parallel behind the curtain. So we just issue a simple command that's transform. One of the things that Spark is really smart about is it won't actually execute any of these transforms until the last minute, till it has to, till we actually force it to return the results to us. And that's nice because by piling up these transforms, it can do a number of things. It can optimize and minimize the amount of data shuffling it has to do and the amount of computations it has to do. Any intermediate RDDs that don't need to actually exist, it can not actually create them independently. It can recreate RDDs that are too big to fit around, and it can dispose. It can do a lot of smart stuff. Again, we don't have to worry about it. The programmers did by just lazily evaluating this stuff. So we can add another transform. For example, say that we want to only find the distinct visitors. So repeat visitors we don't care about. We just want to get the distinct visitors. We want to boil it down. So we can do another transform to boil things down. We can reduce our data here, and it'll keep piling up all these transforms, and it won't do anything until we actually ask it to do an action on the data to give us a particular thing, like give me the number of unique US visitors. So when we actually say give us a count, then it will go and do any of the pending transforms, and it can do them in the most efficient manner. So this is the Spark form that we'll find ourselves using. Load the data into RDDs, work on the data while it's in an RDD as much as possible, because this is all parallel. And when we're finally done and the data is boiled down to where it's a manageable amount, then we can say, spit it out to me as a Python list or whatever we want to work with in our script. So this is the formula. We'll find it works very well and very naturally with many, many different kinds of data and different kinds of operation, different kind of projects. This isn't going to be constrained. We're not going to find this pattern to be constraining or inconvenient. So let's look at a simple example here, but it'll introduce a couple of important mechanics up front. So the first thing I said we want to do, we want to suck our data into an RDD. And so let's say we've got a text file sitting around here, a tab separated file. We're going to work with a lot of human readable text files in our exercises because it's nice and convenient to go and if you want to look at the actual data. But again, we'll see that Spark can suck in binary formats and very specific formats if it wants to. But we're going to read in some data from some human readable text file here that happens to be some server log. And we want to read that into an RDD. And we'll find out that one of the very popular and simple commands to use in Spark is to read things from a text file into an RDD. But right away, this does introduce to us the Spark context. So the first thing, though, that Spark has, the object that all of our stuff in Spark is going to kind of derive from that we care about here is the Spark context. This is the machinery behind the scenes. So everything starts out with all that machinery, all that parallel capability, whatever the administrator set up for you to use behind the scenes is all bundled up in the Spark context. And so that's where we're going to start from. We're going to grab some RDDs from the Spark context. Now, if you're using bridges like we all are, whenever you start up the Python shell, the Spark context is automatically there and it's set up. If you're setting stuff up on your laptop, when you install Spark, you can set up the Spark context and it will be there for you as you do all of your examples. If you've got your own cluster back in the department, when you set up Spark or your administrator sets up Spark, you set up all the parallel machinery. So it's automatically there. So it's very straightforward to use. And today, all we're going to need to do is whenever we read data in, we just have to say, hey, Spark context, and it's there for us. Now, if you're writing scripts, this is one little bit of trivia here I'll throw out now, but please don't go too far. I don't want to go too far into the weeds with this. Is that if you're writing scripts, standalone programs, right? We're going to do everything interactively here. But when you're done with this, you might have scripts that you want users or your collaborators in your project to use, or it might be something that you want to run every night, overnight, because it might take 2 hours to run on your data. When you write scripts, the Spark context needs to be defined a little bit more clearly. So if you're going to write a script instead of doing things interactively, you need to include this kind of stuff at the top of the script. It's the only difference from anything we're going to do is if you want to turn these into standalone run on their own scripts, add in a few lines to set up the Spark context. And then you can run the scripts on their own independently like this. So we're going to do everything interactively, which is a wonderful way to work with big data. It's pretty amazing to work with terabyte and petabyte size data sets just interactively and get results back there at your fingertips. But if they need to run offline as scripts, you need a few extra lines in there to get things started. No big deal. But here we are, we're doing things interactively. So we start things up, we read our data in from our disk file into our first RDD. And from there, we're going to successively transform one RDD to the next and get closer and closer to our final results that we want. By the way, I call everything, for your sake, for your clarity, I call everything that's an RDD with this underscore RDD name here. That is not true of normal, Spark scripts. People don't break them out and label them all RDD. So it's up to you to recognize what an RDD is. But just for the sake of the workshop, I label everything that's an RDD as an RDD. So it's very clear to you when we're dealing with RDDs. Okay, now that we're getting into stuff here, it's probably time for me to catch up with some of the Spark specific questions here. Is there an alternative for Spark? We'll talk about some of the alternatives. There's nothing that does quite what Spark does. The only one that I think is really viable these days is Dask, but we'll talk about those at the end of this talk. So that's a good topic, but I'll come back to it specifically. As I was saying before, we have read our data into an RDD. Now it's time for us to do some transforms. And so we have a lot of transforms available to us in Spark. I'll pull up a list of the most common ones, and we'll use many of the most common ones. One of them we'll find is filter. Filter allows us, as the name suggests, to kind of filter some of the elements out. And so in this case, maybe we only care about the visitors that came to our website to look for Hubble related information. So we can filter out the visitors, filter out the lines that don't have Hubble in them. And so we can do that by giving them a little filter function here. Now, we have some pop-ups here which are there for a reason, in particular because lambdas are a little language-specific feature that we'll have to talk about briefly here because we'll find them so incredibly useful with Spark. A lot of places in Spark will have the ability to stick in functions. In this case, a filter says, give me a function that will filter our data. Now, a lot of the times in Spark, in real-world cases, that function is going to be very simple. In this case, the entire function is Hubble in the line. Now, we could write a separate Python function, define a separate Python function that is nothing but this statement right here. Or we could say, that's so simple, let's just inline it right here. And that's where we'll find lambdas to be very, very useful. And you'll find them to be rife throughout Spark programming. So a lambda is just a function that's so simple, it doesn't deserve its own subroutine. It doesn't deserve a name. We're just going to define it right here in line. And so we're going to use those an awful lot. Most languages today have adopted lambdas as a nicety because there's lots of times when you're programming, when you get some simple place where it calls for a function, but the function's so simple, you go, I don't really want to go off and write a whole separate function for this. And a lambda works really well. So we're going to use a lot of lambdas. So just if you're new to Python, this is the syntax. It's very simple. Lambda just says, here is what we're given. So it's going to give, this is the input parameter to a function. If we're writing a function, this would be the input parameter. So Spark is going to give us a bunch of elements to filter. We'll step through these in more detail with some more detailed examples, but it's giving us a bunch of lines, and our entire Python function is just Hubble in line. So if you're not familiar with Python, this is basically just going to be a Boolean true-false function. Is the string Hubble in? So it means, is it actually in the line? So Hubble in line is a true-false function that allows us to filter out all these elements. So we'll come back to this with more examples. I don't want to bog down on it while I'm going through the general process. But the idea is our transform here is saying we're using the filter transform to filter out some lines, and we're going to filter out all the lines that don't have Hubble included in the line. Okay, so we've done successfully a transform on our RDD. Now it's time to actually spit out a result. How many of those were there? And the action in Spark that allows us to count how the number of elements that we have in our RDD is, well, count. So we're going to run the count action on our RDD, and it will tell us 47. So at this point in time, we figured out how many entries in our server log had Hubble in the line, 47. And as a matter of fact, if we want to look at the first entry that somebody visited that had Hubble in the line, we can do another action, which is to take the first element from our Hubble lines RDD. And so we say first, and it pops back the first one. And this is just some string here from our server log here. So it's a GIF. Somebody downloaded the Hubble GIF from our log as they were visiting. Okay, so this is pretty much what we're going to do over and over, but it's going to be more complex and more elaborate. And eventually we can do machine learning techniques and everything else embedded in the middle of this process. But the idea is load your data in an RDD, transform from one RDD to the next as you refine your data down, and eventually spit out some results at the end. Okay, so common transformations that we have here, and there are many more. There's a full list here at the very nice Apache documents. So the nice thing about Spark, it's an Apache project. It's got very good documents for it. Not all Apache projects do, but this one certainly does. It's great documents for this. I recommend as we do exercises, you pull this up in your browser too next to you is to have the Apache documents. You'll see there are lots of transformations, but I'll go over the most important ones here and most common ones. So filter, we just looked at. Filter says, hey, give me a function which will help me to filter out elements. So I take the RDD, and by giving it a function which returns true or false, I end up with an RDD coming back with fewer elements, right? We've thrown out some of them. Map says, give me a function that can transform every element. So maybe give me an RDD that's made up of a bunch of words, and maybe I want to get rid of all the capital letters. So give me a function which converts all strings to lowercase, and I can apply it to all the elements in the RDD. So an RDD has, by the way, the term elements is the standard one that you'll find used. Elements, an RDD has a bunch of elements. That's just saying the pieces, data pieces that make it up. And we'll see RDDs are very flexible. RDD elements could be GIFs, could be WAV files, but we're going to work mostly with text, for our simple examples to begin with. So, you can say, give me, if I've got an RDD, it's a bunch of words, then for each element that the function's going to be given, give me back maybe all those elements converted to lowercase. So I might want to map everything to lowercase. I don't want to deal with upper and lowercase strings. So map gives me back an RDD with the same number of elements. Filter is going to reject some elements. And an important one, which is maybe the most confusing to beginners, but it's important, is flat map. Flat map says, hey, for every element, you might give me back multiple elements. I might get back more elements than I started with. And this is really useful. The most common case would be if you start out with a bunch of lines of text and you want to break it up into words, something we'll find very useful in our first example, our first exercise. If you've got, if we read in a bunch of lines and each element is a line, which is what the text read will do by default, and maybe we want to break it up into words. That means by start out, I might have 7,000 lines of text, but my new RDD might be 15,000 words, which means I need a function that can give me back multiple items, and then I end up with more elements in my resulting RDD. So these are three very common type of things to do on elements. We can also say, give me back only the distinct entries, get rid of the redundant ones. That'll give me back an RDD with the redundant ones eliminated. I can also do all kinds of sampling stuff. As we know in big data and anything dealing with statistics, sampling is important. So, and sampling also has a lot of options attached to it. There's lots of different ways you might want to sample things. So there's lots of options here that are interesting and important. We can sample an RDD. We might start with an RDD that's got several billion elements to it because we're dealing with big data. And we might say, I want to sample that down to some smaller subset. I can take and combine RDDs with unions. I can get the intersection of them, just the common elements. I can subtract one from another. I can do a Cartesian combination, which means all the possible combinations of two. You want to be careful about doing this on big data. And this last one's really simple-minded, but pretty important for our example problems. I can create an RDD from scratch with just a list that I can give it of elements right in place. So when you're going in the middle of your script, if you want to just create a little RDD with 5 elements that you would just want to put there in your script, I can just parallelize a Python list into an RDD because we want to turn that in. We want everything to be an RDD as we manipulate it. So if I got a Python list of things, but I want it to now come into play with my Spark calculations, I want to parallelize it and do a little 5-element RDD. So these are some very common transformations we'll find ourselves using a lot. Okay, well, to continue then, there are also actions. These are the things, right, so transforms get us from one RDD to the next. Actions get us our results back when we're done and it's time to grab them. So a very maybe basic fundamental one is collect. Give us all the elements of the RDD that's typically the last one. When we're finally distilled down, we got our last RDD. Maybe we started out with a billion elements in some big data set, and we're finally at the end, we got our top 10 results here. We can just collect those and that will spit them all back out. So collect will give you all the elements in RDD. You don't want to collect on a big RDD. You only want to collect on your final results. Count will give us the number of elements in an RDD. And that you can do on a big RDD. You can do that. You might want to do that on a big RDD to make sure that, hey, I got a billion elements. It's not time to collect things yet. So you're doing your analysis. You start at the billion. You do some filtering. You're like, did I really weed this down? You can do a count and go, oh, I'm down to 200 million. Well, it's probably not time to collect things yet. Let's keep filtering stuff down. So you can count at any point in time and see what you've got as a sanity check. You can count by value. So you can look at how many times any particular entry, if it appears in RDD. Then we come on to one that's very important here, and is maybe the most important concept in all of big data that for new people that are new to data, big data and data analytics, which is reduce. Reduce is any time we want to take and we want to collect down boil the data set down by applying one function to it so that all the elements combine down into eventually one element, for example. I've just made that seem much more complicated than it is. Let me start off by saying very common examples of reductions are sums, minimums, and maximums. So if we have a data set, and we want to find the sum on all the elements in that data set, that's a reduction. We're taking all the elements and we're reducing them down to one sum. If we have a bunch of elements, we want to find the minimum from all those elements. We've got a billion elements. We want to find the smallest one. There are a billion integers. We do a minimum. That's reducing all the elements down to one. Reduce is when we want to combine all the elements down. Now, the way that we work with those operations with big data is that we want to give a function to Spark that says how to combine any two elements, how to do the reduce operation, any two elements. Only two elements. That's all we think about is two elements at a time, because then it can go out and apply that in parallel. And that's much more efficient. So in other words, when we talk about summing a billion elements, what we do to Spark is we just tell it, hey, we want you to add any two elements, and go and keep repeating that until those billion elements are reduced down to one sum. Or if we want to find a minimum, we just tell it, take the minimum of any two elements, and then you end up with one element. Keep applying that until you're down to one. And the reason we take this approach is that it's much more natural, actually, when working in parallel and working with big data sets. For example, if everybody out there, if we were all in a lecture hall right now, if we were back in the pre-COVID days, and we're all in a lecture hall, and there are 400 of you out there, and we want to get the sum from all the people in the audience, I could either say, everybody stand up one at a time and tell me your sum, and it would take me 400 steps to get that sum. Or I could say, everybody turn to your neighbor and add your sums together. And boom, in one step, we're down to 200 sums. Now I could say, everybody with a result, turn to your neighbor and add your sums together. Now in 2 steps, we're down to 100 sums. And in 8 steps, we could get our answer. So you can see combining things 2 at a time is a much more efficient way to do things. The same with minimum, right? If we had 400 people and I want the minimum in the room, I could say, everybody turn to your neighbor. Whoever's got the minimum, keep your number. The other person, you're done. And we could, again, in 8 steps, have the minimum number. That'd be much easier than me going through all 400 people and keeping track of what the minimum is. So reduces are thought of in terms of binary computation, combining any two elements together. And then we tell Spark, you go off and keep doing that until you get me your answer. So reduces are very, very common to parallel computing in general, but for purposes of our workshop here, to big data. So in big data world, we think of reduces as how do we combine any two elements, and then we tell the system to go out and keep doing that. The most common ones, again, are going to be sum, minimum, and maximum. Okay, we also have first, again, common actions. We've got lots more actions that you can go find in the documentation, but these are some very common ones. Whenever we got a big RDD, it might, again, have a billion elements, but we want to make sure that we're doing the right thing. We just transformed all of our elements from mixed case to lowercase, right? So we had a billion elements and we just made them all lowercase. Well, we still got a billion elements, so we don't want to just collect them all and look to see if they're lowercase, but I might want to take the first 20 of them and make sure they all got converted to lowercase. I can do that. That's not going to overwhelm me. So I can say take 20. And that will, out of our billion element RDD, spit back the first 20. And I can go, oh, there, look, they're all lowercase. I did the right thing. So when you're working in Spark, a very, very convenient, common thing to do is every time you do a transform, maybe take a few of them as a peek to see that you did the right thing, especially when you're developing your algorithm. So today, while you're working on Spark as new people, every time you do a transform, it wouldn't hurt to take an element or two to make sure you did the right thing. We can also take the highest ones. We can take samples. We can save the whole thing out. So we can do lots of other stuff. But we're going to find these operations here at the top are very, very powerful and very useful and very common. I have an RDD with 2 fields and wanted to create a third field. Would I use an action or a transformation? So you've got an RDD. So it's a good question. We've got an RDD with two fields, say that produces X and Y, and we want to create a new field, Z. It's the sum maybe of X and Y. Okay, well, do I want to use a transform or an action? Okay, well, first of all, you want to go from one RDD to another RDD. So we want to use a transform. You're anticipating my next slide. Transformations get us from one RDD to another. Actions will bring us back to data. So from what you're asking, it's a good question, we want to create a third field. So we want to create a new RDD with a third field. So we want to do a transformation. Okay. Now, okay, what kind of transformation are we doing? We want to go the same number of elements. You want to go from an element that was XY to one that's XYZ. So that sounds an awful lot like a map. Indeed, that's exactly what you want. So you're going to write a function to do this. You're going to write a simple function, and it might be so simple, just a lambda is what I would do. But you're going to write a simple function that says, given each element with X and Y, give me a new element with X and Y, and the Z being X plus Y, which will be Z. So simplest function. It takes an input element in and spits back a new element that's got 3 pieces instead of 2. Very simple function. It maps one element to the next, so it's a mapping. And so that's what you'd have. You'd have a map, which is that very simple. Again, I'd do it as a lambda because it's so simple. And would just be saying, for element, give me, XY, XY plus X plus Y. So it'd be the tuple with XY, X plus Y, which is what it would return. So transformations, again, get us from one RDD to the next. Actions will spit our results out at the end. Transformations, piling up one transformation to the next is a great thing to do as we work on our data, because Spark will wait until it's forced to finally evaluate all of those, and then it can do a lot of smart things. Actions are what you pretty much want to use towards the end whenever you finally have your answer, because again, in big data land, we're starting out with billions of elements maybe, and so we don't want to collect everything and try to look at results until we're down to some manageable chunk of data that we've got, the final report. Maybe a dozen things you spit out on the screen, or maybe a couple megabytes of data that you write to disk, but certainly not the billions of elements you had to start with. So you pretty much trigger your actions at the end to collect all the results and spit it back out. Although along the way, it can be very helpful to do a quick count or a quick take as you're doing your transforms, just to kind of make sure that you're doing what you think you're doing with your transforms. It's an easy way to check. Okay, now, we're running out of time. I want to get the first exercise before lunch. But an important topic, because it's very, very useful, will show up again and again as you analyze data, is the fact that Spark can automatically work very comfortably with key value data sets. It just calls them pair RDDs. That's just the terminology you'll find in the documents. And it basically says anytime you've got a Spark RDD where you can guarantee that all the elements are made up of 2 pieces, then it magically is a pair RDD. And you have some special transforms and operations that make sense for key value pairs that we can also use. So you don't have to do anything special to make an RDD into a pair RDD, as long as it just happens to contain all key value pairs. So on the language side, actually, it's just tuples with 2 pieces to them. So if we've got an RDD and all the elements happen to have 2 pieces, then we can use some of these key value operations from the regular world of key value data manipulation. We can do things like, we can sort by key, and it'll use the first, by the way, the first one's always the key and the second one's the value. So with key value RDDs, first one's a key, second one's a value. So we can do things like reduce by key. We can combine all the common key values together. We can group things by key. We can sort them by key. So you can do neat things with key value type of data that you would, you can just treat your RDD now as a key value database. Automatically, if everything is just, again, 2 pieces, it's automatically a key value database, and we can do this kind of stuff. Now, all the regular transformations are available as well. Now, the neat thing about this leads us in the direction of actual dealing with 2 sets of key value databases. So if we have 2 RDDs, 2 pair RDDs, this is actually now leads us automatically, we find ourselves in the world of kind of classic database table type operations where we can do joins and stuff like this. So those of you that are experienced database administrators that have worked with SQL type databases are going to be very comfortable with this kind of stuff. Those of you that are new to us, well, get comfortable with it. I'm going to introduce a topic here because it's going to be recurring constantly as we work with data. We're going to find ourselves wanting to do these operations, which at first sound like they've got very limited usefulness, in particular join. It seems like, how often would I want to do this operation right here? If you just read the description of it, it seems kind of very specific and odd. But again, anybody out there that's got experience in database land says, oh, joins are a core of working with data sets. So anytime we've got two RDDs, where they're both these pair type RDDs, they're both key value RDDs, we have the ability to use these operations on the RDDs. Let's take a look at these, because I'm telling you they're really useful and it sounds really abstract. We're going to find ourselves even in our basic exercises here using them. Let me give you the first simple example we'll come across. So if we've got a simple database here, we've got a database of our top purchasing customers, and it's in our RDD. So here's our best customers, our top purchasing customers. And by the way, we look at this. This is automatically, without us making any effort, it's a pair RDD. It's a key value RDD. The key is the first one, in this case, the names, and the value is the second one, in this case, some amounts, what they purchased. So we have an RDD that just naturally is a pair RDD. Now we have a second RDD here. That's the names with the addresses. So, and it's not all the same. They don't all share the same elements in here. Some of these appear here and some of them do not appear. This is all of our customers. These are our top customers. But we only want to send out promotions maybe to our top customers. So we say, okay, how do we combine? How do we extract just the ones that are common to these two RDDs out of here with their address information and how much we want to promote to them, how important they are to us? Well, if we think about this and we think about this and think about this, we would find ourselves wanting to do this join operation right here. Again, it sounds kind of, if we describe it like what it's actually doing, it sounds pretty abstract. But if we describe it instead of just saying, hey, just find me all the common keys out of these two RDDs and combine their data, because that's what this type of join is doing. Find me all the common keys and combine their data. Then by doing the join, I end up with this. I found all the common keys. So Bob and Joe and Alice were common between these, whereas Frank was not. So Frank didn't make it through. The join got me all the common keys, Joe and Alice and Bob, and it combined for each one of their keys, the data from both RDDs. So for Alice, it combined the data that was the number data, and it combined the address data. So that's what a join does. And again, if you're new to this stuff, you might think, I don't need that for my analysis. You're going to be amazed how often this kind of combination of two data sets together becomes useful. In this case here, for our little mailing list application. So we're going to do a join here. We do the join between the two key value RDDs, the two pair RDDs, which is what Spark likes to call them, but it just means they were two key value RDDs, and we get our answer. So we're going to find ourselves doing this a lot. As a matter of fact, on our exercise that we're getting to just in time to do it before our break. So I'll hold off on the questions till I introduce the exercise here quickly. So we're going to do some data analytics on Shakespeare's complete works. By the way, this is actually a valid academic field. People are doing this stuff now, trying to analyze Shakespeare's works to answer previously difficult to answer questions. Did Shakespeare really write his works? That's something that's in question, believe it or not, amongst academics. At any rate, we're going to analyze this stuff, and we're going to do it with Spark here. And as we do it, I hope that many of you are going to say, as we do these simple exercises, Shakespeare one, you're going to say, I could do this with some other stuff I know how to do. I know some Python library that would allow me to do this easily. I can even just write some straight Python code to do this kind of stuff if I wanted to. The important thing to recognize here is not that we happen to be working on Shakespeare. It's that the technique we're using here for Shakespeare, which might only be 15 megabytes or whatever it is, would also work with a data set that's 15 terabytes or 15 petabytes. So the techniques we're using scale up. So yes, what we're going to do here, you could do with pandas, you could do with just some Python. It'd be the equivalent of asking your librarian some questions about Shakespeare. She could open up Shakespeare and dig through it and say, yeah, I think there are this many plays, or I counted how many times he said, Othello, So yes, a librarian could do that by hand. But the same code you're writing here, just run on an enormous data set, could answer those kind of questions about much, much bigger data sets. So don't get distracted and say, I know other ways to do this. Ask yourself if the other ways are scalable up to big data. And the answer is almost certainly going to be no. Okay, here's our problem. Here's what we're going to do. So here's our exercise. By the way, I recognize our break is coming up right now. The break is not the exercise time. For those of you that have nothing better to do, you can do it. But we have dedicated exercise time right after the break. So you're going to have plenty of support and exercise time after the break. I respect our break time. So I'm not taking it for granted. Okay, here's our exercise. We've got this input file. You've got it sitting around now in your Shakespeare directory in the exercises folder. It's also, you can find that out here if you wanted to, but it's sitting in your exercises folder. And while you're doing this, as I mentioned, having the Spark document open in your browser next to you is a useful thing to have. Between the Spark documents and my slides, you've got a lot to refer to here as we do our first exercise. To start this exercise, you're going to want to make sure you're on a compute node. So if you didn't already grab yourself an interact node, do it. By the way, if you don't know if you're on an interact node or not, if the command prompt says login, then it's the login node. It's not interact node. If the command prompt says something like R485, then it's a compute node. So if the command prompt right now says login, make sure you type interact to get a compute node before you start trying to do this, or things won't work right. If you're already on an interact node, you're going to be fine. Go into our big data directory, and the Shakespeare folder is where we want to be, because that's where our data set's sitting. If you don't do this right, things won't work out. In particular, when it loads this in, it'll be empty, and then you'll be very confused. So make sure you're in the right subdirectory to load this. Load the Spark module, because that loads all the Spark software we're going to need, the whole Spark stack, and then type PySpark, and that will start up the Python Spark shell. And so that'll allow us to do things interactively. Once you do that, the first command you want to type to load in the data set will be this. You want to load in the Shakespeare file into your first RDD. So I'm giving you the first command. But then here's some exercises for us to work through. So the first thing to do is to count the number of lines. So what transformer action do you have available to you that might give us how many lines we've read in with this command? Then we want to count the number of words. Well, text file reads in lines. So I'm asking you for the number of words. So we need to somehow or other break things up, split them. So if you're new to Python, split by is a big workhorse in Python for dealing with strings. It splits strings up. So I'm going to give you that as a little hint. If you're a Python person, you of course have come across split many a times to deal with strings. So split will split some strings up into pieces, because we definitely want to split things up to count the number of individual words. Now, how many unique words are there? So we don't care about redundant words. We want to know the number of unique words. These first three are pretty straightforward here. These next two, I break them out separately. They're a little bit harder. They're a good bit harder, but they're important. So you're going to find these a little bit more challenging. Count the occurrence of each word. So how many times does each word occur? And show the top 5 out of that list. Once you count the occurrence of each word, find me the top 5 most occurring words. Okay, so these last two, like I said, they're a bit challenging. So if you were an experienced data scientist, you might find yourself automatically approaching this problem by thinking of it as a key value pair, because ultimately that's what I'm asking you for. I'm asking for how many times does each word occur. That looks like a key value list to me. So you might find yourself, but you're new to this, so that's not going to spring naturally to mind. So I'm going to give you that hint. So you might want to think about, it's not the only way you could go. There are multiple ways to do this, but you might find it a good way to do it. So think about where you ultimately want to end up with your data. What's the final result? And then think about the transforms that will get you there. So my ultimate result, I look at it and think of it as a key value data type thing. And so I say, how can I transform things to get there? So think about that. This is a very, very common situation to find yourself in when dealing with data and trying to get a result, squeeze a result out of a large data set. You should think about, what's my result? How do I transform to get there? And what's the form of my final result that gives me some guidance as the kind of intermediate data I want to find myself in. So this is our exercise. Okay, so here's my answer. And again, your solution does not have to look like this. There are more than, it's more than one way to approach this. However, here's what I did. And we can talk about this line by line. We will, especially to answer some pending questions. So everybody, I think, read in the text file correctly. Although again, some of you noticed that if you say if you misread this or something else, it might not have errored right here immediately, because once again, it's a transform. Until you actually try to do something with it, Spark may not actually execute this. It waits until the last moment to execute stuff. But at any rate, we read in the text file here. Now we can get the number of lines, because it's the first thing to do, as simply as count the number of elements. Text file reads in line by line. We just do a count. This is the number of lines we've got right here. So we got 124,000 some lines. Now we want to get words. So this is the first thing that's a little bit challenging here. And so I know that I've got coming into it however many lines, 124,000 lines. I know that my next RDD I'm transforming from this is going to have more elements, because we're breaking the lines up into words. Right away, that tells me I'm probably using a flat map here, right? Flat map is the one that gives you more elements back. Okay, so that was the big clue here, that I want more elements back. As a matter of fact, this particular use case of breaking a string up into multiple pieces is the most common use that you're going to come across for something like this. So we need a flat map. Okay, that's the first part of it. I need a flat map. Now, flat map says, give me a function such that I'll give you every element and you give me however many elements you want back, however you want me to break this thing up. So in this case here, it's a very simple function. So I'm just going to make a lambda. And again, the way lambdas work in Python is this first thing is the argument, the input argument. If we wrote this out as a full function, this would be the input argument right here. So we're giving it each element x, and we simply want, the only thing we want this entire function to do is just to split each element up into its pieces. And again, in Python, the split command for strings is pretty common, pretty widely used. So any Python people undoubtedly know this if you're new to Python. That's why I gave you the hint, but it's, again, you're learning something new here on the fly. So I hope you were able to kind of figure this out. But that's exactly what's happening here is we got a flat map that says, hey, break each element into potentially more elements. And what function does that? Well, this function right here. And it's a simple function. So it's just a lambda where it says for every element, split it up into pieces and give me that back. So that's all we need to do to transform from the lines into the words. And if we do, we can check that, we can verify we did the right thing and also get our answer here by just doing a count of that and see how many words there are, 904,000 words. So please stare at this and make sure you're comfortable with this because this is, pretty basic stuff we're going to build on here. Now we say, okay, we got the trickier things, the trickier questions. Ultimately, question 5 is really give me the word counts for each one of the words. And this is, the answer is going to look something like this. It's going to have a word and a count, and we're going to sort them in order, as a matter of fact. So I know I want to end up with a ranked list like this. This is where I want to end up. So when you're thinking about Spark and data transforms, and quite commonly for data analytics in general, you look at your end result, look at your starting data, and start to say, how do I get there? Well, I look at my end result, and one of the things that immediately occurs to anybody that works with a lot of data is that I'm staring at a key value pair. That's what I've got. I'm staring at key value pair. So that should pop out. Now it does, for many of you, again, you're new to this, so it's going to take a little while for that to sink in, but after you get experience working with data, the obvious, most important, overwhelming characteristic of this is a key value pair. I got a key and a value. You can actually debate which one's the key and the value. Of course, with Spark, the first one's the key and the second one's the value, but we could switch them and still that would be valid, but we got a key value pair. We got pairs of everything. That's what our data is. So this is where I want to get. So I know I want to end up with key value data. So how do I get the key value data from a bunch of individual words? Okay, well, and by the way, we could use count by value, but it's an action, and some of you stumbled across this. I think somebody asked this question. Somebody usually does. If you stumble, you wander around inside the Spark documentation, you'll notice there's a count by value, and you might say, okay, I can count by value. The problem with that is that this is count by value is an action. It's a thing that spits out at the end of your calculation, the final result. So whenever you're working in Spark, you want to keep everything in the RDDs until you have your final answer. You don't want to start spitting intermediate results out because then you have to, first of all, there's two problems with that. If I'm working with RDDs and I spit an action out with a substantial amount of data, if it's really big data, and it's hundreds of millions of elements or whatever, now I've got something that's going to overload the memory of my computer, my front end node. It's too much to deal with. I keep everything in RDDs until you finally get things down to the final answer. That's, first of all, the general approach that you take in working with big data. Everything stays in RDD until you're done. And some of the actions that spit out intermediate results like this are obviously not going to do that. They're going to spit back things as a Python data structure. In this case, we're going to get a dictionary of results back. So that's not good to begin with because it's probably in a real big data case going to be enormous. It's too big. You don't work half in Spark and half in Python. It's not the way you work, except because it's going to overwhelm your serial front end Python script that's running away there. No, you want to keep everything in RDDs and work with those with all the parallel machinery. The second reason that's bad is if we do get intermediate results back into Python, and you think you're going to do some stuff in Python and some stuff in Spark. Well, when you get stuff back into Python and you start manipulating it there because that's what you think you're comfortable with, I know how to use this Python library to do some analysis on this intermediate data, even assuming it's not too big to work with. Then you got this intermediate data. Now you got to get it back into an RDD, and that's an effort. So in general, your approach should be, I want to keep everything in the RDDs and use RDD transforms to work on my data until I'm done and I finally have my answer. So we don't want to go wandering around finding ways we can do part of it here in Python and part of it in Spark. And instead, we want to keep everything in RDD. So I know that I want to end up with these key value pairs at the end. And I know I have a bunch of words right now that aren't key value pairs. They're just words. They're just keys or just values. They're just one piece of data per element. For key value, I need that to be 2. I need to convert my words into key values. Well, you can just simply, again, you're new to this, so it probably doesn't occur to you, or you might think that's weird or that's not right. But if you work with data and you know something's on its way to being key value, you just simply convert it into key value data. I just took all my words and I took and turned them all into a word and a count for that word of 1. So every word is getting a count of 1 associated with it. I know I'm going to combine all these counts together to get the real counts later, but at the moment, I just want to turn them into key value data. So I can start to manipulate them as key value data. So I just made them into key value data. How did I do that? I did it with this map command right here. So this map command said, I'm going to give you an element, X, and you give me back whatever the transformed element is. So I gave it back X with a count of 1. So this map went through all the elements and applied this map to it. And the map it applied was this very simple function here, this nameless lambda function, where it said for every X, I'm going to give you back X comma 1, a little tuple with X and a count. So a bunch of words came into this, and this is what came back out. The with a count of 1, project with a count of 1, Gutenberg with a count of 1. All of my words with a count of 1. So that got me into key value data. So I'm heading down the right path here. Now I want to go and combine all the thes out there and get a count for them. So I want to combine all the thes. I want to reduce them all down so that all the thes are a single the with appropriate count. Okay, right away, that tells me I want to do a reduce. Again, the reduce operation is fundamental to, I could say, parallel computing in general, since I do lots of parallel computing of all different sorts, but certainly in big data, it is valid as as the number one way to say to distill data down. We want to reduce our data down. We want to combine the data in some simple way. And this simple way is just we want to add all the ones together, and that'll give us a total count of thes. Every time we combine 2 thes together, you want to think of reduce as operating on 2 things. So we have a bunch of thes out there. And when we combine 2 of them together, it'll take the 2 thes and combine the 2 ones together. It'll combine the values together to give us a 2. And then now we've got a bunch of thes with 2s out there. Now, when we do combine those together, it'll take 2 thes with a count of 2 together and get a count of 4. So, and you don't have to worry about the odd counts out there. If there's like a the with a count of 3 and a the with a count of 2, it'll combine them together and get a count of 5. All we need to do, though, is tell it how to combine any 2 of those. And that's what we do with our reduce right here. We have a very simple function that says, given the value X and the value Y, how do you combine them together? Well, in our case, we're just doing a sum, X plus Y. So again, reduce by key is saying you can give me any fancy function you want as long as it tells you how to combine the values together. And in general, it's going to be very simple. It's going to be a minimum or maximum or a sum, but you can get fancier and you'll occasionally see some weird logic combinations and whatnot. But in our case, we just want the sum. So we do a reduce by key. So it'll take all the keys uniquely and combine them together. So it'll only do all the thes and all the projects and combine them together. And what do we want to combine their values? So we reduce the values by key, and we end up with something that looks like this. Now, along the way here, I want to make sure I know what I'm doing. So I didn't have to do this take here, but I did this take to make sure I did the right thing. So I did the take up here. As I said, when you're working through this stuff, anytime you do a transform, it doesn't hurt here to do a little take and make sure that you're heading in the right direction. So I did a take here, and I said, oh, looks like I'm doing the right thing. It looks like I have 11 counts of the word fawn, 1 count of considered with this hyphen on the end. Again, we're ignoring weird punctuation, everything. We're not going to fight with it just yet. Fame, mustachio had a count of 1, not too surprising. So it looks like I'm on the right track. So I reduced it down, and I've now got pretty close to what I want for my final answer. Okay, so now we have a bunch of words with a count associated with them. So we're most of the way there. We now want to sort them. Only if I go to sort them, I'll notice that the foremost, if I don't dig too deeply, I'll see sort by key is the first thing that pops up. If I dig really, really deeply, there's a sort by value we could use, but we don't want to use it actually, and we want to use sort by key, and we want to get comfortable with swapping keys and values. So the way I'm going to do it is the recommended way to do it is I say, I want to sort by keys. The reason you want to sort by keys is key value is not just a key value database. The key is the handle to the data. The key is what's associated with the hash. The function behind the scenes that knows how to get to the data works with the key. The value can be anything. It doesn't care about the values, but the key is the handle to the data. You want to work with the keys. Anytime you're working with key value data, not just in Spark, but anywhere, you want to work with the keys to grab the data by. So for example, to sort things, we really want to sort with the keys because that's what the system knows. If you sort by values, to find a value, a particular value, pretty much you have to go through all the keys. You have to exhaustively search. There's no efficient way to find a particular value in a key value database of any sort, Spark or otherwise. You can find a key very effectively because the system has organized things by keys. It knows how to find the keys. But to find a value, you have to search through everything. So we'd like to sort by keys. Well, in this case here, unfortunately, the values are the values are the keys and the keys are the values, right? The key is the word, but I want to sort on the word count. So I could scratch my head. I could dig a little deeper and find there is hidden away. There's the sort by value function. Some of you may have used it. No big deal. But for me, as a data scientist, I go, oh, I've come across this problem many a time where my key and my value, I would prefer that they were the opposite. I would prefer that my value were my key and my key were my value. It's not an uncommon thing, manipulation, to want to do when you're working with key value stores. You want to flip them. And it's trivial, wherever you're working, it's trivial to flip them. In Spark, we can do it very simply, just like this. We can say, I want to do a map where I flip the keys and the values. So here's my map. I just want to take every key and every value and flip the two. So given an element X, given a tuple X, I want to take and flip the first element into the second and the second into the first. So here's a map that just flips key values. And I can see if I take a few of them afterwards, I can see I did exactly what I wanted to do. I flipped the keys and the values. Right? So this is a common enough operation. Anytime I find myself wishing that my keys were my values, I can do this. And I did that, and now I can sort by key. And this is going to be very fast and efficient. And this works. Now, as I said, some of you may have dug through the documentation, good for you, and found there is a sort by value. And you know what? If you look at the source for sort by value, which by the way, you can do, this stuff's written in Scala. And Scala, probably none of you use Scala. It's kind of a very niche language, but it's not complete gibberish. And if you look at it, you can very easily see, you know what sort by value does? It does exactly what we just did here. It flips the keys and the values and then does a sort by key and then flips them back for us. So that's what it does. So you can sort by value if you want. But in general, you should get comfortable with the notion that whenever you find yourself wishing that the keys were the values, just flip them. And I did that. And then I sorted by key. False just means sort in ascending order descending order. So sort these in descending order. And indeed it did it. And if I take the first 5 of them, I can see I got what I wanted. The is the most common word with 23,000 some occurrences. I has 19,000 some, and et cetera, et cetera. So these last steps here do some things that, again, you should get comfortable with if you want to be a data scientist and you want to work with data, but are probably not obvious to you if this is your first experience with this kind of stuff. So turning things into key value pairs, well, you can always do that with data if you know that's the direction it's heading. The reduce operation is a very common thing. Although if it's new to you now, it sounds like it's exotic, but it's a very common thing to do. And flipping keys and values. These are common things to do. Talk about this last line in a second, but these are very common things to do. So get comfortable with the concept whenever you find yourself manipulating data and saying, keys and key values are backwards. Oh, fix it. And so these are common operations. Now at the bottom here, I point out that you can actually combine all of these things together. You can string methods together, like in most object-oriented languages. In Python, you're certainly welcome to string all these methods together. And so I do this entire thing here as a single liner down here. That is not a particularly friendly way to do things, but sometimes it is reasonable to do it. Like up here, you notice I took the distinct words and I took the count right away. I strung these two methods together. So feel free to do it where it makes sense and makes nice readable and manageable code. Don't be ridiculous like this, although you can do it. This does, like I said, the whole thing in one fell swoop. So I hope you're comfortable with this. And if you're not, we can come back and answer questions about this as much as we have to. But let's look at some ways we can expand on this particular problem a little bit. So here's some homework problems for you. The first one, and somebody asked about this, was, hey, we've got punctuation here, and it does noisy up our results a little bit. Sticking you'll notice that, for example, the word here and the word here with a period would show up as two separate words. That's not really what you probably want. So we can go to the next step and clean this up a little bit. So we could remove punctuation. You could do that with some mapping and filtering of your own, or as somebody else pointed out in the comments, there are regular expressions which are Python. Part of Python is are something you can apply as well in these filters. So you can get pretty fancy with getting rid of punctuation any way you want, or you can do it in a pretty crude, straightforward form of just, hey, filter out periods, filter out this, filter out that. But at any rate, that's a good beginner problem, is to attack this, is to get rid of the punctuation that's mucking up our word counts. Now, the next thing you might notice is that an awful lot of our popular words, our most common words, are simple-minded ones like da, and that very often when people are doing text analytics, they don't care about. They don't care about what they call stop words. And so is there a way to remove them? Well, you could write, again, a filter of your own that started to get rid of some short list that you had. And that would probably work, and you might want to try that. On the other hand, let me introduce the concept that there are fantastic natural language processing libraries in Spark that allow you to start to do some of these tasks in a much cleaner and more portable way. So for example, the natural language toolkit that we can import here would allow us to start to get rid of these with stop words remover, for example. And that gets rid of just stop words. And it also works with different languages. That's a nice thing about it. So it knows the stop words for various languages. So this would be an easy way to approach this problem. Now, the next step might be that you want to, recognize that words like run and running are, for many analysis purposes, the same word. Well, this all of a sudden something you don't want to code up yourself. But if you start thinking about it, all the irregular words that you have in any language are a real pain, and it's difficult to do. And so you'd like to somebody to do that for you. Well, fortunately for you, Natural Language Toolkit has a stemmer. Stemmers do exactly this. It has a variety of them, as a matter of fact, because different stemmers take different approaches. A very popular one is the Porter stemmer. So if you want to use that from the Natural Language Toolkit stemmer options, you can bring that in, and that's very easy to use. And so you might want to give that a shot here too. And so now we're starting to do some real text analytics here. And that's important. And a lot of the tools are right there at your fingertips for you to bring in and use with Spark. And again, you might say, oh, I can use these tools elsewhere too. The difference is here, we're using them in a parallel way. You don't have to worry about this working in parallel. Anything that's in an RDD is going to work in parallel and scale up to huge data sets. So this is something that you can run on your laptop, yeah, but you can also apply it to an enormous corpus of text, and it will still run in parallel. So we're using all these nice libraries and tools, but we're getting all this parallel stuff for free because we're working in Spark. Let me briefly cover some random topics I've kind of gathered together here that are all concerned with optimizations. I don't want to spend a lot of time on them because many of you will find that Spark is very efficient and does this optimization well enough by default that you don't want to concern yourself with digging into it. On the other hand, it is nice to know that when things aren't working exactly as you would prefer, that you're not just helpless. Too often, if you use something, if I'm using something in say NumPy and it's not working right, and all I can do is just hope, because I can't go in and rewrite the library, and you're not going to go in and start fixing Spark problems. Instead, it's nice when you have exposed to you functions that allow you to optimize when you want to, and you can completely ignore them most of the time. Most of you will never use any of these functions, but I'm going to mention them quickly for those of you that do. And especially if you find yourself in a really mission critical application somewhere, and it's really important, and you know that something should only take 10 minutes to run and it's taking 3 days to run, it's nice to not just be helpless. And so here are some optimization tools that you can use. A very simple and easy one is that you can give Spark some suggestions as to where RDDs, how useful and immediately important they are, what their priorities should be, and how they should be cached so they might hang around a little bit more, because Spark has the ability to, when it runs out of RAM, to push things off into disk space. But sometimes you might know, because of the way data is combined or used later on, you might know that something's important to keep around. You might give Spark the suggestion to keep things in memory, if possible only. Or maybe something's low priority, and you can say, keep this on disk only. It really doesn't deserve the memory space. And so Spark does its good job of using its own cache type algorithms, recently access, temporal access, and spatial access, and everything else to try to figure out where to keep things. But you might be smarter than Spark about something, and you can give it these suggestions. And it's very simple. You can just tell it to persist an RDD with certain levels, storage levels, and it will do its best to do that. And if you guess wrong, you're not going to crash things. It will just not be able to honor what you're asking for, but you can give it some help. Likewise, Spark distributes your data of the RDDs across all the disks and RAM behind the scenes and tries to match it up with cores to process the data. And, you know, it does a pretty good job of it in general, you hope. But you might know something about the way your data groups together and is operated on that's smarter than it can figure out, in which case you can come up with your own partitioners and tell it how to split things up across the RDDs. You can define that if you want. Most of you will never want to do that. If you want to go even lower level and do some parallel programming type approaches to things, you can do that. You can say, okay, here's some routines I want to run in parallel out on the cores that I've got behind the scenes on the data individually, in which case you get some classic parallel programming techniques that sound familiar to those of you that come to our parallel programming courses. You see these kind of things here where we can accumulate things, we can broadcast data out there. And this can be, again, really a good optimization if you think like a parallel programmer, and occasionally you think of a way you would do this with parallel programming, that Spark might not be smart enough to recognize the opportunity to apply that algorithm. So you can get as low level as you want without having to dive into this, the scale of source code for Spark. So this is neat. Again, if you're a parallel programmer, it's nice to know you can do that. Maybe most important for those of you, though, that suspect you're running into a performance problem is to check it out and see where time is being spent. If you do, I really have a performance problem, or is this just the best we can do? And Spark has both some capabilities to change the configuration. There are a lot of options there you can tweak and play with and try to suggest configuration optimizations to it, as well as a web interface that's very easy for you to just see where it's spending time as it's doing these transforms, and you can begin to home in on where your time is going. Oh, that doesn't look right. I think maybe there is an optimization problem there. Well, we need more RAM, or I should persist, whatever. The point is that it's not difficult to investigate where the time is going with Spark. It's got a very nice web interface that you can get to. So those are optimization things many of you may never care about, but for me, it's very comforting to know that when I do run into performance problems, it's not just, well, it's a black box and you can't help. You can absolutely do that here. I/O formats. I've already mentioned to you that beyond text, Spark is capable of sucking in data from a lot of other different formats directly, and that is a wonderful thing. It prevents you from having to write all kinds of connector code and write scripts to transform data. And as a matter of fact, you'll find that Spark is ready to pull in data from some very complex formats that you might even think of as kind of proprietary in the sense they're not really generally exposing what the protocols and the formats are to you, but Spark can read them just fine. And some stuff that is pretty much exposed, like JSON, but also a lot of database formats that are straight up difficult to parse. It can read in directly. That is an incredibly powerful and wonderful and convenient thing. It can even read in things like compressed files directly. That's nice. And in the same vein, it can also read from a variety of file systems. I've mentioned to you, HDFF is very often the backing file system for a lot of Hadoop installations because it gives you a nice, well-understood parallel file system, distributed file system, but your local just drive will work fine. If you install Spark on your laptop to do toy problems, and many of you might find that a convenient thing to do just to play around with this, it's happy to use your local drive. Now, things won't scale up. Your performance will be dismal for any large problems, but hey, it'll work and let you, do toy problems. On the other hand, if you want to go in the cloud direction, you can use Amazon S3, for example. It's happy to connect directly to Amazon S3 instances, in the cloud. I think, Lustre, for example, is our file system on bridges. Lustre's a large parallel file system with great performance. That's kind of file system you'd like to back things on big supercomputers and whatnot. So at any rate, Spark has excellent support for all of these kinds of file systems as well as formats. Now, what about data that's not sitting there in a file just ready to be processed in, offline? What about this real-time streaming stuff I mentioned earlier? Spark also has streaming capabilities built into it, which are, again, incredibly helpful because when you might think anybody can do streaming, all it is like batch processing, except I just read a little chunk at a time in real time. And that naive approach won't get you very far once you run into the real world of things like failures and timeouts, which happen with streaming data, load balancing, because if your streaming data isn't always the same cadence, same bandwidth, integration with, you've got static, data that's sitting around, you've got the streaming data, and very often you want to combine the two and log stuff and doing that is not trivial. If you just switch everything over to this batch approach, and integration with the other components too, which is really important that we're going to talk about later on, like the machine learning stuff. This is all built into the Spark streaming. So if you are dealing with streaming data, increasingly people are, that's a wonderful capability. And it is a very rapidly evolving area, and it's an increasing trend of people dealing with streaming data. The last number I saw last year, I grabbed a number that's pretty credible from a nice review article, and I was saying about 15% of the global data, in some sense, is currently real time, and that number is absolutely growing. The trend is on an upward curve. So streaming data is really important. I mentioned earlier instruments that do a lot of streaming out there in the scientific community. So far, we've just dealt with straight, simple RDDs, which underlie Spark. We're going to talk about data frames here, and they build on top. Behind them are RDDs. However, as the world got a little bit more realistic from the initial no SQL enthusiasm of we're going to throw out SQL and tables and just everything's going to be key value stores, people realized that data does have a structure to it in general. Very often, data does look like some kind of table, and you do have some kind of fields. And not only is that helpful for our human intuition in dealing with it and code management, because things start to look a little bit saner and better organized, but it can really tremendously aid the optimization of the Spark system or anything that's dealing with data. Because if you actually know what your data format is, if I actually know that something is a string and something is a floating point number, I can make a lot more, I can optimize my code a lot better than if everything is just a generic object. And while Spark is happy to let you cram anything you want at each element, one element can be, like I said, a GIF, and the next element can be a wave file, and the next element can be a floating point number. That is very difficult to optimize for, as opposed to if I know that every single element is a 32-bit floating point number. Now I know how much data space to allocate and what buffer sizes to do and what kind of methods to call. So actually knowing what my data types are is a tremendous optimization. It's one of the foremost reasons why dynamic languages like Python that have performance issues, because having the requirement that everything can be a random object is very difficult to optimize for. So Spark can deal with that, but it also would like if you could actually tell it what your data format is. And you would like that because, hey, it's nice to be able to define what fields are if I'm actually dealing with regular records. And we can do that, and data frames are the way we deal with that. As a matter of fact, if you've been leafing around the API, the documents already, you may have already stumbled across a few references where it says, hey, this is the data frame based method to use here. And as we get into machine learning, we'll see a lot of the machine learning things have the generic RDD version and then the data frame based version, because the data frame version is almost preferred and it's going to be more efficient. In this case, because Java underlies, the Java virtual machine underlies this. The Scala runs in the Java virtual machine typically, and because the virtual machine likes to know what the data types are, can optimize much better, it's happy if you use data frames. So we've used RDDs so far because it makes life simple. It's the easiest way to get off the ground. It avoids a lot of errors that we'd have otherwise. But here's how easy it is to use data frames. It's very, very simple. All we need to do to go between an RDD, a generic RDD, and a data frame is just make sure that all of our elements are the same structure in our RDD. So in this case here, all of our elements in this RDD are a string, another string, and we can even separate the strings what they are: a name, and a street name, and a state, and a zip code, right? So if we can assure Spark that all of our elements have this structure, then it's trivial to make this into a data frame. We just say, hey, turn this row RDD into a data frame. It's that simple. Now we've got data frames, and data frames bring along a whole lot more nice structured data manipulation to them. They start to look a lot like pandas, say, from that many of you may have used. And now we can do something like say, hey, show the structure of this, and it'll show us exactly what our data looks like. So it's very trivial to go from an RDD to data frame as long as your RDD does have this regular structure. And a lot of times your data will, because you aren't dealing with random data where one thing's a GIF and the next element's a wave file. Instead, most of the time, or much of the time, you're going to deal with things where you got a couple data points. They're 3 floating point numbers, an integer, and a string. And then if you can assure Spark of that, it can do good optimization. And so, you can even create data frames just without a schema, and it'll by default define fields to things, and that's fine as well. And you can create them inline, like we have the parallelize to create RDDs. We can create, here's a data frame, directly created So it's very easy to deal with data frames. It's trivial. There's also a variation that you'll notice again in the documentation called data sets. And that is for languages that actually have strong typing like Java and Scala. Static typing is really what they are. Languages that have static typing can even detect stuff at compile time. So that's data sets. So that's kind of, think of this as the stricter version of data frames as data sets. That's not relevant for Python, which we're using here because Python doesn't have strong static typing. So, we've said, hey, there's lots of other alternative things as we wander through the Shakespeare, natural language stuff. I brought in some libraries. You might have seen those before elsewhere. I mentioned now data frames are looking kind of like pandas, right? But again, keep in mind that everything we're doing here, every RDD can be terabytes in size. That's why this is called big data. That's why you came here. It's a big data course. It's not just I'm showing you some nifty and convenient libraries to analyze, a couple 100,000 lines of Shakespeare. I'm showing you libraries that will allow you to work on your complex multi-petabyte file sets. Every RDD we have could be huge. Every transform we do could use thousands of cores in parallel to do the analyses that we're to do. We haven't done any complex analysis so far, just some mappings and whatnot. We're about to use the machine learning stuff though, and we're going to see some real analyses. Every algorithm we do from all of those can grab the memory and the cores and everything else magically for you. You don't need to worry about it. It's the same code you'd run on your laptop, only now it's going to run 10,000 times faster with 1,000 times more memory. Okay. Let's see. The question earlier was, what are some alternatives to Spark? And the answer is really there's nothing else that really has credibility at large scale. And I encourage you to be skeptical about anybody's opinions in computer science in general and data science in particular, including mine. So be skeptical of what I'm telling you and do 5 minutes of research before you commit yourself to months and months of working with a particular technology on your project, or maybe years. Absolutely, don't disagree with me, but be skeptical of what I'm telling you and go look around, because what I'm telling you is that every successful large-scale project right now is pretty much using Spark, unless it's an older one that was using Hadoop. There are a million other approaches out there that people are swearing are going to be successful or superior in one way or another, but see what successful actual deployed applications they have before you take that too seriously. So don't just take somebody's toy example that works great or their assurance that it's a superior approach and the world will adopt it. Instead, I suggest that you look and say, what is actually being used out there to do large-scale data analytics? And the answer is almost invariably Spark, with some exceptions that are being done in Dask. I think it's the only other one that's got any traction. And Dask is an attempt to do the same kind of parallelization things we're doing in Spark, only to retain more of the laptop feel of a Python, pandas code running on your laptop. And so Dask approach instead is to try to parallelize a lot of NumPy-based stuff and data frames-based stuff at that level and make those things work in parallel piecemeal, piece by piece, library by library. And so if you can use those, if the ones that have been successfully Daskified for you work well, that can be a very simple, low effort way to get from a typical piece of laptop code into something that scales up and parallelizes some. So some pieces of scikit-learn, for example, which is very useful. We'll talk a lot about scikit-learn tomorrow. So, sometimes Dask can be a very low barrier of entry to get some stuff to parallelize. Now, I could talk about this in a lot more depth if people are interested in this. There are drawbacks to this. Dask is very small and lightweight, but has a lot fewer features. And if pieces haven't been converted to parallel, there's nothing you can do. It's not like in Spark, everything's already parallel. If you use it, it's going to work. It's not, you're more dependent upon pieces having been converted. And Spark is definitely old, more dominant. It's, it's more mature. So you're not going to have to worry about finding pieces as much. The main difference, I think, is that Spark has, the main difference for me, I think, and many of you in use cases, is Spark has a good SQL optimizer. So SQL type searches, we talked about data frames, and you're going to start doing SQL type queries on those data frames. Spark has a serious SQL optimizer built into it for that. That's very, very important. Dask doesn't have that at all. So for any pandas kind of things, you don't have that capability. And that is bad news for performance reasons. So that's maybe the biggest drawback to Dask. But You know, academic projects, a lot of them can entertain more risk than industry. So you might want to give it a shot. It might be a quick way to get off the ground. I also earlier had a footnote. I didn't highlight it, but it was in the notes that the guy that invented pandas has a lot to talk about with pandas optimization. His article was famously titled Top 10 Things I Hate About Pandas. But it's, you know, it's a little bit overblown, a little hyped, I think, to get eyeballs on his article. But he does have some good explanations as to where you're going to run into optimization issues if you start out with low-level stuff, in particular pandas in his case. And it's the guy that created pandas, so he's, you know, he knows what he's talking about. But again, it's a trade-off. Don't take anybody's word for this stuff. Go and do some research. Spend a few minutes in Google finding real-world results, not academic articles and not endorsements and enthusiastic blogs. Spend a few minutes finding real-world results before you invest in any technology in data science. Okay, let's see. The last thing I'll talk about here before we dive into the machine learning, straight up machine learning, is that if you want to run these programs, now that we're starting to write some more complex programs, you might not want to cut and paste everything. So if you want to run the examples that are sitting around in your directory, the easiest way in Python, at least with Python 3, it used to be simpler in Python 2. With Python 3, the easiest way to run these scripts is to run this command right here and stick in the script name right here. So for example, the clustering script that we're about to jump into, which has, you know, it's a little bit more than you want to cut and paste maybe, you can run the script within the shell and get the results. So this can save you cutting and pasting if you just want to run the scripts. So keep this in mind as we look at some more complicated programs, and they're all sitting there inside of your directory. Now that we have a toehold into big data, now we're going to look at what a lot of people think is the interesting part, which is to start to apply machine learning algorithms to that big data. And although manipulating the big data in and of itself is pretty amazing when you think about the power that you've learned now, which again is to deal with these petabyte-sized data sets or 100 terabyte-sized data sets in an interactive shell, or scripts, but to deal with things feasibly that are enormous. So you've got just for data manipulation, a tremendous amount of capability right now already that you didn't have starting out earlier today.